Hi everyone, and thanks for joining me in this video on error analysis. And in this video, we're going to look at uncertainty. Whenever we make a measurement, we don't really measure the true value. We measure close. There's always some error. It's impossible to measure properties exactly. Here's an example where we're measuring a Viking. And we're using a tape measure. And you don't want to get too close to the Viking because he's got a sword. So we've got to estimate how tall this Viking is. So there are errors in our measuring device. We're using a tape measure and it slides really easily. So there's a problem with our distance measuring. And then also, do you measure to the top of the Viking or to the top of his horns or what? So there's all sorts of errors that we have based on our estimates. So whenever we make a measurement, we aren't really measuring the true value. We're measuring something close to the true value, and we have some uncertainty. So what we do is we try and provide our best estimate of our measurement, what we think is close to the true value. And then if several people make several different measurements, well, are they wrong? They're in the ballpark. They're pretty close. What we need to do is state the uncertainty of each measurement. And looking at this, you can see that there is a region where the measurements overlap, and probably that is where the true value lies. So whenever we state a measurement, we have to give our best estimate, in other words, the measured value that we actually took. And then also we have to provide some uncertainty, and that's usually plus or minus some value. And that uncertainty is also known as the absolute error. When we define discrepancy, what we mean is the difference between two measured values of the same parameter. So looking at the measurement of a Viking, we had 62.2 and 61.4. The difference between those two is 0.8, and that is your discrepancy. We say the discrepancy is significant if there is no single value which is compatible with both measurements. Looking at this ruler, you can see that our first measurement, 62.2, has an uncertainty or absolute error of plus or minus 0.2 inches. And the other measurement is 61.4 plus or minus 0.4. When we plot that on the ruler, you can see that there is no overlap between these two measurements. So that means that the discrepancy is significant. There is no two values. These two values do not overlap, and there's not an area where they are the same. We say the discrepancy is insignificant if there is compatible measurements. So looking at this, you can see that the two uncertainties we estimated came up with a bigger uncertainty, and it looks like they do overlap. And that region where they overlap, somewhere between 61.5 up to 62, that's probably where the true value is. Another thing we need to be concerned with or need to look at is fractional uncertainties. When we make measurements, sometimes our measurements, if we have uncertainty, the uncertainty is a bigger proportion for smaller objects than it is for larger objects. So if you're measuring an ant and you're off by an inch, that's a much bigger proportion than if you're measuring an elephant and you're off by an inch. So the best way to get a handle on this is fractional uncertainty. And what that is you take your uncertainty, your absolute error, your absolute uncertainty, and divide it by the value that you measured, your parameter. And of course, we put absolute value symbol to indicate that the fractional uncertainty is always positive. Here's an example of fractional uncertainty. Let's take the Viking measurement. We measured the Viking to be 61.4 inches, plus or minus 0.6 inches. When you do that, if you take your absolute uncertainty, your absolute error, divide it by your measurement, that gives you an uncertainty, a fractional uncertainty of 0.009. Or if you want to put in terms of percentage, that would be 0.9%. So those are some ways that we handle uncertainty, and that's how we talk about our measurements.